I would like to thank the organizers for organizing this wonderful program. So I'll be talking about finiteness theorem. So let me just start the first slide with some basic notation. So throughout this talk, X and Y would be complex manifolds, and though not said, they would be connected. I would consider only connected complex manifolds. So OXY would be the space of all holomorphic mappings from X to Y. O star XY would be the space of non-constant holomorphic mappings from X to Y. O dom XY would be the space of dominant holomorphic mappings, that is, those mappings whose range have a non-empty interior. And all these spaces, I will give the compact open topology. So what do I mean by finiteness results? Well, I want to study scenarios under which this space, either O star XY or O dom XY, is just a finite set. So let me give some classical examples of such results. We have the very old Liouville's theorem. If D is a bounded planar domain, then O star CD is empty. There are no non-constant holomorphic mappings from a complex plane to a bounded domain. More deep is the Little Picard theorem, which says that the space of mappings from the space of entire functions which miss 2 points in the complex plane, that's also empty. There are no such things. Then going to Riemann surfaces, we have this classical theorem of Debraj, which says that if R and S are compact Riemann surfaces, both having genus at least 2, then the space of non-constant holomorphic mappings from R into S is finite. And another example is, this is a nice exercise to work out, is the set of non-constant mappings from C minus 0, 1 to itself is also a finite set. So these are some classical results where you have finiteness. Now, the result of Debraj was generalized by Imayoshi in 1982 to non-compact Riemann surfaces. So you start with any Riemann surface of finite type and let S be a Riemann surface of finite type Gn with 2G minus 2 plus n greater than 0. Then the space of non-constant holomorphic mappings from R into S is a finite set. Let me just define what I mean by a Riemann surface of finite type Gn. It's just a Riemann surface that's biholomorphic to a Riemann surface obtained by removing n points from a compact Riemann surface of genus G. So in all these results, you would notice that there is something in common with the codomain. Not the domain, but the codomain. They are all hyperbolic Riemann surfaces. That means they are covered by the unit disk, all of them. In fact, this is precisely the condition that guarantees that the codomain is covered by the unit disk. So, motivated by these results, Divakaran and I generalized the result of Imayoshi to higher dimensional complex manifolds. So, let me just state the result. Let X be a product of hyperbolic Riemann surfaces of finite type, and let Y be omega quotiented by gamma be an m-dimensional complex manifold where omega is a bounded domain and gamma is a fixed point free discrete subgroup of the automorphism group of omega. I will explain the terminology in the next few slides, so please bear with me. If n is a tautly embedded complex submanifold of Y, then O dom Xn is a finite set. If Y is geometrically finite and omega is complete hyperbolic, then O dom Xy is a finite set. In addition to the conditions in 2, if the essential boundary dimension of omega is 0, then the space of non-constant holomorphic mappings from X to Y is a finite set. So let me make a remark here. So this is, I am considering a product of hyperbolic Riemann surfaces. So essentially I can view this as Dn quotiented by a product group, right? So you can also ask, what if instead of starting with Dn quotiented by a product group, what if I take the ball and quotiented by a fixed point free subgroup? So that was dealt with by a mathematician named Shiga. So the same result is true also when you replace Dn by the unit ball. But one advantage of the proof that I'm going to sort of sketch is that it directly gives Imayoshi's result, Debraj's result, as well as Shiga's result in the same technique you can immediately see will work in all three cases. And that's not clear with Shiga's proof, whether that will work in this scenario. Okay, so let me explain the terminology that is used. So let M and N be two Kobayashi hyperbolic complex manifolds. Kobayashi hyperbolic complex manifold just means that the Kobayashi pseudo distance is actually a distance. I will not define what the Kobayashi pseudo distance is for, of course, it's a short talk. So let M and N be Kobayashi hyperbolic manifolds. Then by the distance decreasing property of the Kobayashi distance, we already know that the space OMN is an equicontinuous family. So the next question to ask is, and formulate certain versions of Ascoli-Arzela to answer that question. So the following definitions are motivated by our desire to get a compactness result for this space. When is it relatively compact? When the space of holomorphic functions is relatively compact. A subset F of the space of continuous mappings from M to N is said to be a normal family if every sequence Fn in F has either a subsequence that converges uniformly on compacts or has a compactly divergent subsequence. You say the complex manifold N is taut if for every complex manifold M, the set OMN is a normal family. So let N be a complex manifold and let Y be a complex submanifold. We say that Y is tautly embedded in N if every sequence of holomorphic mappings to the smaller space, to the space Y, admits a subsequence that converges to a holomorphic map to the larger space. Then you say it's tautly embedded. So this is an old result that complete hyperbolic manifolds are taut. So this defines the definitions involving tautly embedded and so on. I still need to define those terms like essential boundary dimension and geometrically finite. Those are a bit technical. So what I'll do is I'll give loose descriptions of what they mean, and those who are interested can check out what the precise definitions are. So what you can do is, given any topological manifold, you can consider various connected components after excising a large enough compact set. And those, in a sense, form the various ends of the topological manifold. Now, why is this useful to study the space of ends? Well, all of us have seen the classification of compact surfaces. You would like to classify non-compact surfaces also, and that is done using this. You can get a nice classification result even for non-compact surfaces using the space of ends. You can in fact get a nice compactification of a non-compact surface using the space of ends. So a geometrically finite complex manifold is just a complex manifold which has finitely many ends, and these ends are of satisfy a technical condition. I will not go into what the technical condition is. So there are special manifolds which have finitely many ends, and those ends behave in a nice way. So since I'm being very vague, at least I owe you one example. Riemann surfaces of finite type are all geometrically finite, which is good because and the aim is to recover Imayoshi's result as part of this exercise. Okay, now the essential boundary dimension of a bounded domain in Cn is roughly the maximal dimensional complex manifold that sits on the boundary. So it is not, let me just repeat, it is not, this roughly is crucial. It is not the dimension of the maximal dimension of the complex manifolds that are sitting there, it is roughly that. The actual definitions involves after removing countably many pluripolar sets. So that's because that's a complicated definition, I'm skipping that. Again, for concrete examples, the unit ball in Cn has essential boundary dimension 0. It does not have any complex analytic manifold sitting on the boundary. Same for strictly pseudo-convex domains. And the polydisk has essential boundary dimension n-1. Okay? So now what I'm going to do is I'm going to give a brief sketch of the proof of this result in the absolute simplest scenario, in the scenario of Debraj's theorem. So I will assume X and Y are compact hyperbolic Riemann surfaces. So in that scenario, we need a rigidity result. Let X be d-quotiented by G and Y be d-quotiented by gamma, be compact hyperbolic Riemann surfaces. So G and gamma would be fixed point free discrete subgroups of the automorphism group of the unit disk. If non-constant holomorphic mappings phi and psi from X to Y induce the same homomorphisms from G to gamma, then phi equal to psi. So let me first explain what do I mean by this induced homomorphism. It comes from covering space theory, but let me just recall what it means. So in the previous slide I said if non-constant holomorphic mappings phi and psi induce, it's essentially not phi and psi that will induce the mapping, it will actually be lifts of phi and psi. So you start with X to Y, both of them are covered by the unit disk. You start with the mapping phi. So now what you do is you pick a point X tilde in D, consider a lift phi tilde. Okay. So since this is a lift, you take an element G in G, look at what happens to X tilde under phi tilde and look at what happens to G of X tilde under phi tilde. Both of them will have to map to the same orbit under the group gamma because it's a lift. Since that happens, there has to be an element H that takes phi tilde of X tilde to phi tilde of G of X tilde, simply because phi tilde is a lift. And this H is independent of the choice of X tilde. Why is that? Well, because what are we doing? We are just considering phi tilde composed with G and H composed with phi tilde, and by the way we have set things up, both of them agree at the point X tilde. Right? And both phi tilde composed with G and H composed with phi tilde are lifts of the same mapping phi that agree at a point, therefore they must be exactly the same function. So this choice of H, given a G there is a H, and this is independent of the choice of the point X tilde, and just what I wrote down will give you this relationship. Phi tilde composed with G is chi of G composed with phi tilde, and you can easily check that this association from G to H gives you a homomorphism of groups. Now there is another way to describe the same thing. Since D is simply connected, these groups G and gamma are nothing but not biholomorphic, sorry. They are isomorphic to the fundamental groups of the space X and Y. And there is a natural isomorphism, capital phi from G to pi 1 XX and capital gamma from pi 1 YY to gamma. Capital lambda from pi 1 YY to gamma. Again, these are not unique isomorphisms. There are choices to be made, right? The way you get the mapping capital phi is that you start with a lift of the point X, look at a loop in pi 1 XX, a representative of a loop, lift that loop, look at the end point, there is a deck transformation that takes this to the end point, and that is the way the map is designed. So when you construct this capital phi, choose your lift of the point X to be X tilde. Similarly, when you construct the map lambda, choose your lift to be the point phi tilde of X tilde. When you do that, the map, you can check that the map gamma composed with phi star, where phi star is the push forward, is the induced map on the fundamental groups, composed with capital phi is the required mapping between G and gamma. You can check that both mappings are exactly the same. So this is just a recap of covering space theory. Now that I have this facts from covering space theory, I will sort of sketch the proof in the simplest case when X and Y are compact Riemann surfaces. So look at a sequence of distinct non-constant holomorphic mappings from O in OXY. The aim will be to show that after a point they are all the same, right? And we have this rigidity result that if in some sense at the fundamental group level, both Fk and Fs, let's say for large enough K and S, induce the same mappings at the fundamental group level, then they are the same. That's what the rigidity result says. Not quite, but almost. It says something loosely that. So take a sequence Fk of distinct non-constant holomorphic mappings. Again, because Oxy, Y is hyperbolic, complete hyperbolic, we can assume that Fk converges in the compact open topology to a map F from X to Y. This is because it has to be a normal family and X and Y are both compact, so it cannot have a divergent, compactly divergent subsequence, so it must have a subsequence that converges. Moreover, even though I write compact open topology, because X is compact, this convergence is in fact uniform on the whole of X. Now, the idea is to show that for suitably large K, we can find lifts Fk tilde and F tilde that induce the same homomorphism on G. That will essentially show that after a point, these Fk tildes are all the same, consequently these Fks are all the same. We would have shown that the space is finite. We first choose K suitably large so that Fk of Z, Fk of X, which I call Zk, and Y, which is F of X, both belong to a coordinate ball that is evenly covered, which I call U. So I'm just choosing, wait a second. Okay, so just fix X, fix a point X, I forgot to write that. Fix a point X and just choose K large enough so that Fk of X and F of X are both elements of an evenly covered coordinate ball, which I call U. And choose F tilde and Fk tilde to be lifts of F and Fk such that F tilde of X tilde and Fk tilde of X tilde belong to U tilde. U tilde is just one of the neighborhoods, one of the connected components of the lift of U, that is under the covering map. I choose both lifts to take X tilde to the same point, to the same, same neighborhood, U tilde. And of course, again, it's explanatory, but nevertheless, I should say X tilde lies above X. Okay. Consider the homomorphisms induced by F tilde and Fk tilde, call them chi and chi k. Now, each element of G can be represented by a closed loop at X, say gamma. I'm just using the isomorphism between G and the fundamental group. Then F composed with gamma and Fk composed with gamma are loops based in Y, based at Y and Zk respectively, right? Now, you might think we are done because what happens? Because Fk's converge uniformly to F, it's intuitively clear that F composed with gamma and Fk composed with gamma will be the same loop, and therefore we are done. But actually that's not correct because these two are not even based in the same point. So you cannot really compare what these loops generate in the fundamental group. You have to do something to compare these loops. So what you do is you do the simplest thing. Look at sigma, call F composed with gamma as sigma and define sigma k to be the reverse of delta k and concatenated with Fk composed with gamma, concatenated with delta k, be two loops based at the point Y where delta k is a curve lying in U that connects Y to Zk. Again, I have suppressed the detail here, so essentially I have Y and Zk here, and I'm saying connect by a curve delta k, but U is a coordinate ball, so you could in principle choose an extremely wild loop, wild curve between Zk and Y. I implicitly assume that delta k is chosen nice enough so that delta k, as k goes to infinity, converges uniformly to the constant Y. I'm not mentioning that here, but I choose delta k in a nice way. I don't choose some wild path between the two. Now sigma k converges to sigma uniformly because I have chosen delta k in such a way, and fk composed with gamma anyway converges to f composed with gamma. So sigma k converges to sigma uniformly. Therefore, sigma and sigma k are in the sense equivalent in pi 1 of yy for suitably large k. Okay. So since these two loops sigma k and sigma get arbitrarily close to each other, it's not difficult to show that they are the same. They the same loop at the fundamental group level. Now what you do is you consider lifts of both sigma and sigma k that begin at the point f tilde of x tilde. I just said that they generate the same element in the fundamental group. That means their lifts must end at the same point, right? So, and this point by the very definition of my map chi must be chi g of f tilde of x tilde. That's the way the map chi was even defined, right? Now, the very last step, the quotient map is a homeomorphism from u tilde to u, and delta k lies entirely in u. That means any lift of delta k that starts at f tilde of x tilde must also lie entirely in u tilde. It cannot go outside u tilde. In particular, it must end in u tilde. Similarly, a lift of delta k reverse that ends in chi g of u tilde must begin in chi g of u tilde for exactly the same reason. So, thus a lift of fk of gamma, starting in u tilde at the point delta k1 must end in a point which lies in chi g of u tilde. So what does all this show? This shows that chi k g of u tilde intersect chi g of u tilde must be non-empty, right? But u is an evenly covered neighborhood, and these are elements in the deck transformation group. That just means that chi k g must be equal to chi g, right? So what I have shown is that given a loop, given how did all this begin? Given an element of G, I looked at a representative of gamma and showed that for suitably large k, chi k of G is equal to chi of G. But the fundamental group is finitely generated because we are on a compact Riemann surface. Therefore, for suitably large k, this will be true for all elements G in the group G. So in short, I have shown that chi k and chi are exactly the same homomorphisms. So by our rigidity result, we are done. We have shown that after a point, fk and f all have to be the same. So net upshot is there are only finitely many holomorphic mappings from x into y. So let me just make one remark. I have skipped over a proof of this rigidity result. This rigidity result will also play a role in the main theorem that I have here, appropriately generalized. Instead of disk, I have polydisk, and here I have an arbitrary bounded domain which satisfies some condition. So how this rigidity result is proved is that the fact that d quotiented by G and d quotiented by gamma are compact hyperbolic Riemann surfaces tells you something about the groups G and gamma. They'll have to be Fuchsian groups of divergence type. So what essentially happens is that they will push, if you take a sequence of elements in G, they will have a subsequence that pushes the whole domain non-tangentially to the boundary. And that allows you to apply a Fatoury's type theorem, and that's essentially the main tool used to prove this. And you have analog of Fatoury's theorem for the polydisk, you have an analog for the unit ball also. So essentially this rigidity results proof is the same. You just look at the proof given by Imayoshi for this result, word for word you copy what he has done and just appropriately change d to dn and just change the reference to a different Fatoury's, and that you're done. But the techniques used by Imayoshi after this is done he continues to use further properties of this Fuchsian group, and that part is not at all clear whether it will be true in higher dimensions. So in particular, I like the simple normal families argument. You recover Imayoshi's result and exactly you just use the same proof, you get a proof when X is actually Bn quotiented by a fixed point free discrete subgroup that behaves nicely. So that's it. I think I'm done.